everyone, my name is Ajay Kumar Dakar. So today I'm going to present slides for the assignment number 6. So let's start with the slide. So these are the topics which I have added in the slides. So I have added some more topics to have better understanding for those topics which are provided in the slide. So let's start with these topics. So the first topic is distributed transaction. So like what is distributed transaction? So let's understand by an example. So let's take an example of a Zomato, like you have ordered something on Zomato. So your request, like you have ordered in pizza from Zomato, so your request will be going is sent to their server. So now their server will be sending multiple requests to many other servers. Like one request can be of verifying your transaction, like which is very crucial in verifying transaction, and one request can be of like we can say to update their inventory, like. The same the so we can understand like this single transaction is going to be happen at many sites. Like one site can be the server of the Zomato, one the other another sites are will be going to the like payment vendor which is going to verify your payment, and one will be of like updating the inventory of the Zomato servers. So all these sites at the end, like they need to uh, check only one thing, that whether the transaction is successful or not, like whether they can whether your food item is ordered or not. So in this way, like we are going to like we can see that a single transaction is distributed over many sites. So in this way we can start with the distributed transactions. So we can go by point. So first point is transaction may occur at many sites. Okay. So how we are going to handle these transactions at many sites? So to handle these things, like each site has one its transaction manager, and one is transaction coordinator. So they have their own works, like transaction manager maintaining a log for recovery, and also to execute concurrent execution of a transaction. And each site has its transaction coordinator, like which is going to start the transaction which originate at that site, and also to distribute sub transactions at appropriate sites for execution, and coordinating the termination of, also to like ensure what protocols we are going to use while terminating each transaction at each site. So how this is going to do how this happens, like we can better understand by this picture. Like here is the transaction coordinator of this computer one. Let's say a request comes here. So now this request requires to distribute its sub transactions to many sites. So at the transaction coordinator simply distributes the sub transaction to each site, and then the transaction manager will be going to execute those transactions, and after at the end transaction coordinator will verify whether the transaction is terminated or not. So in this way, we can betterly understand like how this distributed transaction architecture works. So in this architecture, like each site has its transaction coordinator and transaction manager. Okay, so transaction manager is of just for executing the transaction which are either originated at that site, or can execute the transaction which are originated at other sites also. While transaction coordinator just coordinates like uh, distribute the transaction at appropriate sites. Okay, so let's understand like what is system failure. So there are generally two types of system failure. Like many more system failures are also, like the link and the message protocols. Like so the two of the system failures are the failure of the site. Like let's say your server goes down either due to the power cuttage or something due to internally. So that is called the failure of a site. Or one more problem there is like network partitioning. Like let's say the network of India and America are partitioned, so we are not going to know whether the whether the servers in America are failed, or like we are the network is partitioned. So it is very indistinguishable, like whether the site has failed or network has been partitioned. So these two types of system failure, like very we are unable to distinguish between whether it is a failure of a site or a network partition. And many more like many more failures are also there, but those failures are handled by the IP protocols and our internet system. Okay, so like in that example which I have taken of Zomato, like at the end we need to configure like whether the order is either placed or like not placed. So for those things we have some commit protocols, like whether the transaction at each site has been committed or aborted at all sites. So these protocols confirms that whether the transaction has been committed at each site which has participated in the transaction or aborted at all sites. So here comes the like two-phase commit protocols, like to either to commit at all sites or to abort at all sites. So what is two-phase commit? So execution of protocol will be initiated by the, yeah, of course, the transaction coordinator will initiate this protocol for verifying that whether the transaction has been completed at each site or not, or can be committed or not. So first point is execution of protocol will be initiated by the coordinator after the last step of execution is reached. Protocol will involve all sites at which transactions are executed. Let the transaction coordinator of site SI be CI. So what we are saying that like this, of course, this protocol will involve all sites to know that whether the transaction has been executed or not at all sites. So let's say each site SI. So we are having n sites. So each site SI has a transaction coordinator CI. So we have assumed that here our some assumptions are there, like what in the failed site, like we have talked here like failure of a site. So whenever a site fails, this means that computer has been shut down or it is not working. It is not working means it is not sending any like wrong messages also. It is not sending any wrong messages. So failure of a site means it simply shuts down, like it is not going to do anything uh, more. Like it is not going to harm any of our systems or going to send any messages to our systems. So it is simply shut it down. So that is our assumption. Like the failed site will not going to cause any harm to our other systems by sending incorrect messages or anything. So in this two-phase commit by name, we can understand that there will be two phases. The phase one is for obtaining decision, and phase two will be for recording decision. So what will be going to happen in phase one? So let transaction be T and coordinator of SI at which transaction T originates be CI. So the coordinator asks all participants to prepare to commit. So before sending this message to all the participants, what it does, like the CI adds the prepare T to its logs. That it will be this means that it will be going to send this prepare T message to all the sites at which transaction T has happened. So after adding this log to the record, like after adding this record to the logs, then it will send the prepare T message to all the sites at which T executed. So after sending a message, then each site receives this message, and after receiving this message, transaction manager at that site will be going to respond for that prepare T message. So let's say if the transaction manager unable to execute the transaction, so it can send it can add record no t to its logs and then sets abort t message to CI, or else if the transaction can be committed, then it's like it writes ready t to its logs and sends ready t message to CI. So after sending records to log, it forces all logs to stable storage, then it sends the message. So what this line means, like in this process, like whenever we are going to send the message to like coordinator, so before sending that message, our logs will be forced to the stable storage that this ready message is saved to the stable storage before sending this message to coordinator. Okay, so in phase two, like phase two is a decision taking phase. So In this T can be committed if CI receive like that coordinator receives ready T message from all the participating sites. So if that coordinator receives or ready T message from all the participating sites, then it can simply commit. Or if it is unable to receive a single ready T message from any of the site, then it must need to be aborted at all sites. It must need to be aborted at all sites. So after taking the decision whether to commit or abort, like coordinator adds that decision to the logs and then forces to the stable storage. Then after like adding to the logs, then coordinator informs all the participating sites about the decision. Then participants like whichever participating site, they will receive the like message whether it is committed or aborted. So then that participating sites can take appropriate action according to the commit or abort. Like if that decision is commit, then all the participating sites need to commit, and if that decision is about, then all the participating sites need to be about the transaction. Okay. So for example, let Google have a distributed database where each site is replicate of each other, and coordinator must execute the same transaction on all sites, should commit on all sites or should be aborted on all sites. So this can be taken. So So this was all the two-phase protocols. In the first phase, like we are going to send prepare message to all the participating sites, and then all the participating sites were like decide whether to send ready message or naughty message, ready message or about message to the coordinator based on their transaction. Like okay, so this was the phase one overall. And after sending that message, the coordinator decides whether to commit or abort that transaction, whole transaction. And after taking the decision, it spreads the decision to all the sites. So this was all about the two-phase protocol. So by the name, we can understand that it has only two phases. So let's proceed. So like how this two-phase protocol, like how we are going to handle failures in this two-phase protocol. So let's see. Let's take an example of site failure. Like coordinator is still working, but one of the site has failed. So if the site contains committee or abortee message, then it means that the T has been completed, because if the committee or abortee message are added, then that means like there is nothing to do with the transaction. If that site does not contain any of the committee or abortee message, then it will look for the ready message. If the ready message is in their logs, then it will simply ask the coordinator to tell like whether the transaction has been committed or aborted. So else aborted, so undo T. So if committed, redo T, and else aborted, undo T. Okay. So if site does not contain even ready message, then it means like that site haven't sent any message, like haven't replied back to it. Okay, the log contains naughty means that he is aborted. So like if that site does not contain the ready message, that means that site have not replied back to the coordinator for the prepared message. If the site haven't replied back for the prepared message, then definitely coordinator cannot commit the transaction, because it haven't got a ready message from all the transactions, sorry, from all the sites. So definitely CI must have aborted the transaction, so site must undo T, because the transaction is already aborted. Okay, so now this was all about the like when the site fails. Like let's look for when the coordinator fails. So how they are going to handle when coordinator fails. So in this case, like whenever a coordinator fail, it is simply like understand the situation from the participating sites or active sites, we can say, to know that whether the transaction is committed or not. So from any of the active side, if it can sees that the committee or abortee message, sorry, committee or abortee record in logs, then definitely the transaction has been committed, because this committee or abortee message have been added to logs only after the that coordinator sends the committee or abortee message to them. So if there is committee or abortee message, then that transaction is already completed in the coordinator also. So they then it does not have to do anything. If any of the sites contain ready does not contain. Okay, so let's say in all the participating sites, let's say there is one site which does not contain ready message. uh, this is I'm talking only when there is no committee or abortive message in any of the site. Okay, in any of the site, if in any of the site does not contain, like if it does not find committee or abortive message, then it will look for the ready message. If any of the site does not contain ready message, sorry, I am speaking message every time, but it is log. So committee log and abortive log. If any of the site does not contain ready to log, ready to record in their log, so then the coordinator simply understand that it cannot be committed. Like if any of the site does not contain ready to message, then that message, ready to message, was not been sent to coordinator for the reply of prepared to message. So this will simply mean that transaction T is aborted. Else, if all the sites have ready to record in their logs, then the simply it will like recover from that situation, because all the sites have sent the ready to message to the coordinator, but coordinator has been failed after that without sending the committee or abortive message. So like coordinator will recover from the situation for till the time all the active sites need to wait for the coordinator to recover. Okay, so this is the problem. Like all the active sites had to wait for the uh, like transaction coordinator to recover. So that's why. Okay, so this was the problem in this. And now network partitioning. What happens if the network is partitioned? If the network is partitioned and all the participating sites and coordinator are in the single network, then there is no problem because they are already connected. Let's say if the coordinator and some of the active sites have been has been separated due to the network partition. So then the network which has the coordinator, so coordinator will think that some of the participating sites have been failed working. So it will not proceed because some of the sites have been failed. So it cannot proceed further. And what the other sites which are not connected to coordinator will think that coordinator have been failed, so they will also stop, but nothing harm to the system happens because both have been stopped. Like coordinator cannot proceed because none of the sites have been working. All like some of the sites are failed, and the sites which are not connected to coordinator will think that coordinator has stopped working, and they will be like probably waiting for the coordinator to recover. So both the situation do not cause any harm to the system, but both are waiting for each other. Okay, due to the network partitioning. So let's look at the new topic, concurrency control. Require manager. So we need to we will require a manager to handle logs. So either we can have a single log manager or a distributed log manager. In the single log manager, we will fix a single site that will only handles the logs for all the sites. So that is single log manager that resides in a single site. And distributed log manager, each site has its own log manager. So the single log manager scheme is very simple, like that is easy to code and easy to handle all the situations. But in the distributed log manager, we require some difficulty. We need to have some algorithms for to handle that log schemes and all on all the sites. because each site has its own lock manager. So the variants of distributed lock manager, there are generally four types of protocol which we have for distributed lock manager. One is primary copy, one is majority protocol, bias protocol, and quorum consensus. So we will not going to be we will not going to discuss primary copy, but we will discuss about majority protocol and bias protocol and quorum consensus. What is majority protocol? In majority protocol, lock manager at each site maintains a lock and unlock request for data items stored at that site. And so, for each site has its own lock manager. So, for simply for an unreplicated data, that means that data exists at only single site. So, that is simply we can handle by just sending log request to single data manager. But in case when the data item queue is stored at more than one site, that is n number of sites have data item queue, so we need to put logs on according to this majority protocol. We need to put log request on more than half of n sites, and the transaction does not operate on queue until log is operated on majority of sites. So let's say there are 10 sites, so the protocol will not execute on a data item queue until it gets lock on more than five five sites. Okay. So what are the benefits? The benefits can be used even when some sites are failed. Of course, like let's say in case of if we are having 10 sites, then if two or three sites fail, then it will not going to affect our request. It will simply proceed because if two or three sites have failed, so it will simply get the log request from seven. It can simply log the data item on seven sites. So it will follow the majority. So in this way, like if the some sites have failed, so uh, still our system will be available. And what are the drawbacks? Lots of messages and potential deadlock. So let's say if a single transaction happening at there are three transactions in our system. Let's say all the three transactions have one third lock on on some data item. Then of course they are in the deadlock situation because each transaction has one third of locks of that data item queue. So definitely they will not get locks further because all the three transactions are waiting for each other to release locks, and that will not going to happen. So that is a deadlock situation. So that is the drawback of this majority protocol, but there are benefits. Like if some sites have been failed, so still our like concurrency will be maintained. Okay. So another protocol is bias protocol. So requests for shared and exclusive logs are handled differently. So in this bias protocol, we have separated the shared logs and exclusive logs. Like for the shared logs, initially we have also seen that like for the shared logs, we do not maintain, we don't need to have that much concurrency in the shared logs, but for the exclusive logs, we need to maintain a lot of more accuracy because that are going to handle the writes on the data items. So that's why we have biased our system for the shared logs and exclusive logs differently. So for so in this bias protocol, if any transaction wants to have lock on data item queue, so it simply requests lock on any one of the sites, and if it gets the lock from that site, then uh, it will simply proceed. Okay, that means it has locked it has shared lock on the data item. It only needs to get lock on single replica of that item queue, and in the data exclusive logs to lock data item queue, it need to request lock on all the sites, and if all the sites have if it gets lock on all the sites, then only it will proceed on data item queue. So in this there is a benefit like for the shared logs we don't need to uh, like uh, uh, mm, obtain lock on each side, but for the exclusive lock we need to obtain lock on each side. Okay, so in shared lock we only need to get lock on any one of the side, but in exclusive lock we need to get lock on all of the sides. So for the shared logs the overhead is very less, but for the writing it has too much overhead because it is sending too much messages to all the sites, and also the lots of overhead for exclusive logs. So now the quorum consensus protocol comes. So it is like both the majority protocols and bias protocols. So majority protocols have its benefit, like some if some sites are failed, still it will be running in the perfect state, because still it will be running, and there are drawbacks, that was the potential deadlock and lots of messages. And in the bias protocol there was a benefit, like we have very less overhead for shared lock, but there is also a problem with this, like for the exclusive locks we need to it is unable to handle that, unable to handle that if some sites failed, it will unable to handle exclusive lock for the data item queue. Okay, so this majority protocol can handle even if some sites are failed, but this bias protocol unable to handle exclusive locks if some sites are failed. Okay, so now comes the quorum consensus protocol, which is mixture of both majority and bias protocol. So each site is assigned a weight and as with the total of all site weights. So two values QR and QWs are chosen, such that this can be chosen for the for shared lock must acquire lock on enough replicas that the sum of site weights is greater than equals to QR, and for the exclusive lock it needs to have greater than equals to QW. So by adjusting weights we can simply adjust that how many replicas to be logged for shared lock and how many replicas to be logged for exclusive log. So let's take an example. The Google database has total of 10 sites. Each site is a replica of each other, and each site has its weight 1. Okay. So and now takes the QR as 3 and QW as 8. So by satisfying this expression, we can say that 3 plus 8 is greater than 10, and also 2 into 8 is 16, which is greater than 10. Okay, so for read we require at least 3 sites to get log for shared log. To acquire shared log, we need to have shared log on at least three of the sites, and for the write we require at least 8 of the sites. Okay, for write we need to have exclusive log on at least at least 8 sites. Okay, so this were all the like majority protocol, bias protocol, and quorum consensus protocol. Now comes the trading consistency for availability. So first understand like what do you mean by high availability? High availability means when like in this first we need to understand two terms, like what is availability and what is consistency. So the availability means system is always able to process request in zero downtime, like that means high availability. High availability means our system is always ready to process our request, while low availability means there would be a time when our system would not be able to process our request, so that is low availability. We have seen this type of situations many time in our banking system also, like there is a downtime for our banking system where we are unable to process our request of transactions from bank to bank or UPI transactions also. Okay, so high availability means zero downtime. And what is consistency? We have already seen what is consistency, but here means like the strong consistency means all the sites have the same data at the same time. Like whichever time I check the data, take data from any of the replica, I would get the same data. Okay, so if all the sites have the same data, then that means our system is highly consistent. Okay, so here strong consistency means all the sites have the same data at the same time. And also the schedule with read and write operations on the replicated data should give final state equals to, that is the concurrency. So we need to maintain concurrency also for the consistency. So weak consistency has many forms. However, strong consistency has single form, but weak consistency has many forms. So let's talk like what is pure escape theorem. So we have talked about consistency, what is consistency, what is availability, and what is partition tolerance. So in partition tolerance, like our system is able to handle network partitions also. So network partition, If systems are separated by the network, then they are unable to contact each other, then our system able to handle that situations also. So we have talked about consistency, availability, and partition tolerances. So what Brewer's Cape theorem says that according to it, we cannot have more than two of these properties. Like we can at most have any two of these properties. Let's say if we have consistency and availability. So for consistency, that we in our all the sites we are having same copies. That means all sites have the same data at any point of data at any point of time, and availability means at any point of time our system are able to handle our request, but it will not be able to handle the partition tolerance in that case. If we our system are available at like our system has high availability and high partition tolerance, then we are unable to handle that consistency constraint on. So at any point of time we can have any two of these properties but unable to have third property, that is Brewer's Cape theorem. So we can take any of this example, like whenever we need to think, like we can take, let's take availability and partition tolerance. So our system is always available to handle any type of request, and partition tolerance means our system will be able to tolerate the partitions also, but our system will not be able to get the consistency in that case. We can think in practical scenarios also about this, like how we are going to have the consistency if our network is already partitioned and we also need to have high availability. If we need to have consistency for with partition tolerance, then our system will not be available for a time when the system is in inconsistent state or something. So we can at a time we can have at most two of these properties. Okay, so this is the Brewer's Cap theorem. So for large system, we need to have partition tolerance. So it is obvious, like for our large system, let's say for a Google data servers. So their data servers are present in many countries. Mostly they should be divided by the regions, like Asia region, America region, and the Europe region. So by this type of regions, they have been divided. So definitely partition tolerance should be there because these are very large systems. So we should be able to handle the partition tolerance also. So for large system, partition tolerance is a quite requirement. So we need to like choose which one of this. Like we need to think like whether we need to choose consistency over availability or to choose availability over consistency. Okay, so to choose one, consistency and availability most so this is our topic, that threading consistency for availability. If we want to have a high availability, then we need to suffer from consistency, and if we need to have high consistency, then we need to suffer from availability. To choose one, consistency and availability, most applications choose availability over consistency, like we can say Amazon. And in the Amazon, like we at any point of time we only want that we should be able to order any type of orders. Okay, we should be able to order any item from Amazon. So that is high availability, but they might not be consistent at any point of time. So while applications of bank choose system, they choose consistency over availability. That's why we many times we see downtime in banks also. So where availability is not there, but we actually need high consistency in bank system because we are dealing with the money. Okay. How we how we trade consistency for high availability. So we some of the constraints we allow in our system, that many systems allow weak consistency. That means QR plus QW. If we cannot achieve lock in more than S, then still we should be able to proceed because we have acquired locks on many of the sites. So if QR plus Q, that means like for QR we need to, let's say let's take the same example, like there are 10 centers and each have weight 1, and let's say QR to be 2 and QW to be 4. So if we can here say that QR plus QW is less than 10 and also 2 into QW is less than S, that means 10. So here we can see that many systems allow weak consistencies also. So what is the issue here? That issue here is that our systems are not consistencies. Our systems are not consistent. So whenever we try to read, we can get an older version of the data item also. Also may lead to inconsistent state. But what we do here is eventual consistency. So in between there might be a point where our database our distributed system may not be in the consistent state, but eventually after some time our systems will go into the consistent state just by sharing their updates to each other. So eventual consistency here, at some point of time copies may be inconsistent, but at some later time when no more updates, copies will eventually become consistent. Okay. When no updates occur for a long period, all updates will be propagated to all other sites. So in the middle time, like in between times, we many times our system will not be in the consistent state, but after some time, all the updates will be propagated to all the other sites, and our system will finally will be into the consistent state. Okay. And there is one more thing, like here we have already chosen the partition tolerance, but what if we don't need the we don't have the problem of network partitioning. So in that case we like still we trade our consistency just because for the latency, because to maintain consistency we already have lots of overhead for maintaining consistency across all the data all the distributed systems. So for latency, we sometimes trade off our consistency. So what is latency? The amount of time taken to serve the request, like whatever request I have sent. So whether it is committed or aborted, how much time it will take to know that whether it is committed or aborted. So that is called the latency. So latency time starts from like whenever I put a request on the servers, and in how much time it gets completed. Okay, so that is the latency. So in the systems where network partitioning is not a problem, so we can have a high availability and high consistency, but still we trade off our consistency just to have low latency. Okay, so thank you.